All right, guys, so welcome to part two of lesson one. So let's go ahead and start off with some review about what we talked about last time. All right, so let's go ahead and start off by looking at a graph of a line really quick. My line looks something like this. All right, well, if I were to pick 2 points along this line and then connect those dots with a straight line, that line is what we call a secant line. A secant line has a slope. And the slope of the secant line gives us what's known as the average rate of change. And the way that you find the slope of a secant line is you take the coordinates of each of these 2 points and you just do y2 minus y1 over x2 minus x1. Okay? So that's the secant line gives us the average rate of change when you find its slope using the slope formula, which we learned way back in Algebra 1. Right? Now, that tells us the average rate of change. Really, the slope of a line is the steepness of the line. Now, if you're thinking of this function here, we'll call this red line here f of x. That's my function. Well, starting from the first purple point over here on the left and the second point over here on the right, that purple line has a steepness to it, and that would be the average steepness of that function of the interval. But as you guys can see, the steepness of that line is changing. Here it's really steep, so that would be a big slope. Here it's pretty flat. In fact, it's probably almost zero because there's no steepness at all, and then it goes back to being steep again. So we have a changing slope is what we have here, and that's what causes lines to bend is when they have this changing slope. So when you have a bending line, the best you can do is find an average rate of change, which is an average steepness, unless maybe it's possible to find the slope at a single point. How steep is it right there at that point? In other words, what's the slope of that? Well, we talked about how to find that last time using tables, but basically, if you were to find the steepness of a line at a single point, that gives you what's known as a tangent line. It touches your curve at one single point, and the steepness of that line tells you the slope at that point. So I'm going to call that the tangent line. Now, the tangent line has a slope, and that doesn't tell you the average rate of change over some interval. Instead, it tells you an instantaneous slope. In other words, how fast that function is changing at a given point. So the instantaneous rate of change. Now, there is a way to find the slope of a tangent line, but obviously you can't use the slope formula because the slope formula requires 2 points and a tangent line only provides us with 1. Okay, well, one way you could do it is with the table. That little worksheet that we did at the very beginning of the year where you approximate. Basically, you just find 2 points that are really close together and then find the slope between those, and that can give you a good estimate. But there's actually another way, a better way. And so I'm going to erase that. So instead of getting an approximation, which is a lot of work and it doesn't even give you an exact answer, what we talked about is the way that you can find the slope of a tangent line, also known as the instantaneous rate of change, is with something known as the derivative. The derivative can tell you the instantaneous rate of change at a single point. So we have those two concepts there, instantaneous rates and average rates, and that's where that's our main concept we talked about. Now, when it comes to derivatives, another thing that we talked about was notation. So the notation for derivatives. So if you have this function here, f of x equals y, there's a few ways you could represent the derivative. You could write f prime of x. You could write y prime. You could write the derivative of y with respect to x. Or you could put the derivative of f with respect to x. You could write the derivative with respect to x of your function here. Or you could write this. All of these are just different ways of writing the same thing. And verbally, there's 2 ways you could say it. You could say the derivative of f with respect to x. That's one way to say it. Or you could just say f prime of x. Those are all different ways of saying and writing derivatives. And what is a derivative? A derivative is a function that tells you the instantaneous rate of change of a function at a specific point, which is the slope of its tangent line at that point. So that's our review. That's where we left off. Now we're going to move on to, great, we know how to find the average rate of change using the slope formula. That's from Algebra 1. But how do we find the instantaneous rate of change? Well, that's today's topic. So today's objective is how to find the derivative of three types of functions: constant functions, linear functions, and power functions. Now, another way I could have said this objective is, instead of how to find a derivative, I could have said how to differentiate constant functions, linear functions, and power functions. So that's just some vocabulary for you. This is a noun. A derivative is a thing. Differentiate is a verb. It's finding the derivative. So that being said, let's go ahead and begin. All right, so let's go ahead and start off with our constant rule. This is what's known as a constant function, where c represents a number. So, for example, y equals 2. That's a constant function because there's no variables other than just the y. There's no x variables, so it's what we call a constant function. Now, my goal is I want to know, what is y prime? Well, it helps if you remember what y prime is. What is y prime? Well, y prime is the instantaneous rate of change, also known as the slope of a tangent line. So this one's really kind of simple to see what the derivative is if you just know what the graph of this thing looks like. Let's graph that. Do you guys remember how to graph a constant function? If not, I'll review with you right now. But basically, we're going to put a few dots where y equals 2. So here's where y equals 2 right there. But y also equals 2 here. When x equals 1, y is still 2. Or how about x equals 2? Y is still 2. So you end up with a flat line. I'll color it so it doesn't look like the axis. So there's my function there, y equals 2. Now let me ask you, do you guys remember from pre-calculus, what is the slope of a flat line? The slope of a flat line is always 0. So I've got my answer now. If the slope of my line is 0, that means the instantaneous rate of change is 0. It doesn't matter what this number is. That number could have been something different. It could have been a 5. All that's going to do is make this flat red line go up to a few spaces to y equals 5, but the slope is still going to be 0 because it's still a flat line. So my first rule is known as the constant rule. Anytime you have y equals a number, the derivative is 0. That's simple. The slope is always 0. All right, let's take a look at our next rule, linear functions. This is a linear function. Now you guys might remember linear functions looking like this. I'm going to leave the b out of it for now. We'll learn about where the b comes into play a little bit later. It actually doesn't affect anything at all, but there's a reason for that, and we'll talk about it later. But for the time being, that's a linear function. A linear function, when you graph them, in case you don't recall, they make a line, a straight line again, but it's like a diagonal line. So, for instance, let's say I had y equals, and I'm going to replace the m with a number here. Let's say y equals negative 3x. Well, it's helpful if you guys remember how to graph this in order to find the derivative. I want to know what's the derivative. Now, the derivative, as you guys remember, it's the slope of your line at that point, at any point that's specified, okay? Some of you might already know the answer because of what I just said to you, but if you don't, it's okay. Pay attention here and I'll show you. So let's graph it. I don't have a y-intercept. It's plus 0, if you want to think of it as plus 0, which means that we start at 0. This is my rise over run, so I'm going to go down 3 and over 1. So down 3 over 1 puts me here, and I have that. And so there's the graph of that line. Now I want to know what's y prime, though. How does the graph help me? Well, it helps me if I remember what the slope is. What's the slope of my line? Well, we actually already did it, didn't we? We went down 3 over 1. Now, as you can tell, you actually don't need to graph this at all. You could see the slope. The slope of a linear function is -3. And if the slope of that linear function is -3, guess what? That means the derivative is -3. So here's our rule for constant multiples. Whatever you have, y equals mx, the derivative will be just the m. That's the slope, also known as the instantaneous rate of change. Now, these two names are pretty similar, so I want to make sure you guys understand the difference between them. This is the constant multiple rule because you have a constant multiplying x, whereas the one before it is just called the constant rule because it's just a constant number. There's no variable next to the number at all. So those are different ideas there. So we've learned how to find two derivatives, and they're both pretty straightforward. Anytime you have y equal to a number, the derivative is 0 because that's a flat line. Anytime you have a constant multiplied by x, we could apply the constant multiple rule to realize, oh, the slope just must be the number in front of x, which is 10. Okay, so we have two derivative rules learned so far today. And now I'm going to show you one that's not obvious, one that does not connect to Algebra 1 at all, and it's a little strange. So here it is. This is known as the power rule. So first of all, let's talk about what is a power function. This is a power function. Okay, power functions look like this. So you guys are familiar with this guy, right? Y equals x squared, or how about y equals 7? I'm sorry, not 7. How about y equals x to the 4th? These are all power functions. In fact, you can actually even have a number in the front, which we'll talk about a little bit later. But so long as you have a variable with a power, you may or may not have a coefficient, then you have what's known as a power function. Okay? Now, how do you find the derivative of these things? Well, I can't do a neat little chart here for this one, or a graph, and explain why. In fact, you guys aren't going to actually even be able to know why what I'm about ready to show you works until later on in the year. Okay, so I'm just going to give you a rule. And that's what this whole chapter is about, really. It's just about rules. It's not so much about the why behind it, so much as the rules themselves. So here's the rule. If you have a power function, the derivative will be the following. Whatever your power is, that's going to become a coefficient. The x is going to stay there. And your new power will be 1 less than the original power. So in other words, n minus 1. That's really weird, but there it is. That's the power rule. So let me give you guys a quick little example here. Suppose I told you that y equals x to the 5th power. What would y prime be? Well, I'm going to take the 5 and I'm going to make it a coefficient of x. And then my new power is going to be 1 less than this power. So therefore it's 4. So if my function is y equals x to the 5th, then the derivative of that will be 5x to the 4th power. And that's what we call the power rule, and it applies to power functions. Okay, so that's that. Let's go ahead and let you guys try one of these real quick. So let's find this one. I want to find out what is f prime of x. Notice I'm using f instead of y now. Doesn't matter. They both mean the same thing. If I want to find f prime, pause the video here and see if you could figure out what the derivative will be. All right, so not sure if you're feeling comfortable with it yet, but if not, pay attention. You're going to get more chances to practice today. You're going to put the 2 in the front as a coefficient. You're going to keep the x, and then you're going to take 1 away from the power that's here. So 2 minus 1 is 1. And since it's a 1, we really don't need to write it, so you could technically just write 2x. Okay? So if f of x is equal to x squared, then f prime of x is equal to 2x. Now, I want to try to bring this full circle. In the beginning of our very first math assignment I gave you guys was a worksheet, and it looked something like this. I gave you a point right here, and that point was 2, 4. And what you guys did is you found the slope from this point to 2, 4. Then you found the slope from another point to 2, 4. And then you found the slope of another point to 2, 4. And you just kept going. And one of the things I was trying to illustrate there was that eventually, since these dots are getting closer and closer to the black line, eventually they're just going to converge into one dot, and you're going to end up with a tangent line. And our goal was to figure out what is the slope of our tangent line. Well, I've already told you guys that the slope of a tangent line is your derivative. Now, do you guys remember what the answer was from the worksheet? I told you the function was y equals x squared, and I asked you what is the slope of the tangent line. It was 4, right? Here's how you'd write that, by the way. Y prime at x equals 2, that's this point right here. Y prime at x equals 2 was 4. The derivative at x equals 2 was 4. In other words, the slope of my tangent line at 2 was 4. Now, let me show you how this helps me. What does that have to do with this over here? Okay, well, I want to find what's my derivative, or in other words, my instantaneous rate of change, or my slope, at x equals 2. So I'm going to plug 2 in for x. 2 times 2 is 4. Boom. I've got a formula now that will tell me the slope of my function at any point. I don't have to do a table anymore. Okay, so let's do another explanation here. So same graph, but we were just doing for the point 2, 4, right? We found the slope of that. It was a slope of 4. But what if I asked you guys to find the slope over here? Like, let's just say that was maybe like 525. What would the slope be at that point? What's the slope of that tangent line? Well, instead of doing a whole different table and working this all out in painstaking work, all I really need to do is find the derivative, which we already know is 2x, and plug in the x value that they give us, and it will tell you the slope at that point. The instantaneous rate of change at that point is 10. The steepness of that orange line is over 1 up 10. That's how steep that line would be. And that's the slope of my function. So there you guys have it. So this slide was really just kind of connect the ends together for you. Let's go ahead and actually do a whole bunch of examples now and just kind of look at how various little math things happen along the way and how we're going to deal with it. So I've got some examples over here. I'm going to do an example. I would encourage you guys to write the examples down in your notes. Student practice, I would encourage you guys to write those down in your notes too. But how much work you show for those is really up to you. But make sure that the examples at least are very full and complete, because your notes are one of your study guides, right, for your test. You want to make sure that you have good notes. All right, so let's go into the first one. I'm being asked to differentiate each function below. So I'm going to find v prime of r. Okay, how do I do that? Well, this is a power function. And with a power function, all you do is you take the exponent and you put it in the front, and then you subtract 1 from the power. And there we have it. Another way I could have written this, by the way, would have been like this. There's other ways too, but we'll leave it at that. Okay, so I want you guys to try one. Here we go. H of L is equal to L to the 9th power. Pause the video here. See if you can get the answer. When you're done, unpause it, and I'll have the solution up for you after that. All right, so here's our derivative. H prime of L would be 9L to the 8th. All right, let's go ahead and do the second one. Now, the second one here, part B, has a little bit of a difference to it. It's got a coefficient already in the front. So we're going to learn how to handle that now. So h of t is equal to 3t to the 4th. So how do I find the derivative? Well, I'm going to take my power, and I'm going to make it a coefficient. But uh-oh, there's already a coefficient there. Now, instead of speaking vaguely, but like saying make it a coefficient, I'm going to change how I say it. This is what we're really doing. Instead of making it a coefficient, what we're doing is we're multiplying it to the front. So I'm going to take my 4, and I'm going to multiply it to the front. And then we take 1 off of the power. So multiply the power to the front, and then take 1 off of the power, and you get this. 4 times 3, which is 12t cubed. And there's my derivative. This is a formula. that will tell me the slope of this function at any given point. All right, so let's have you guys try one of those. Go ahead and pause the video here and see if you guys can find the derivative of g. When you unpause it, I'll go over the answer. Here we go. So g prime of x, I'm going to multiply the 3 times the 8. You don't want to write it like this because that looks like it's 3 minus 8, right? So what I would encourage you to do is to go ahead and put maybe this thing in parentheses. I don't know. I just wouldn't put 3 minus 8 because that looks like my subtraction, right? And then we're going to take 1 away from the power, which is 2. So we have 3 times negative 8, which is negative 24, and then we have x squared. So that's our final answer there for the derivative of the g function. All right, let's go ahead and take a look at C and D. C and D are what we do when we're dealing with fractions. Fractions, a lot of people don't like them, so we need to spend a little bit of time on those. So let's say I have a coefficient that's a fraction this time. Well, it doesn't actually change the process. It just means you have to know how to work with fractions. So if I want to find the derivative, I'm still going to take my power and multiply it to the front. And I'm still going to take 1 away from the power and get 2. The issue is, do you remember how to do this? Well, when you're multiplying fractions, you think of both of them as fractions. And there's 2 ways you could do it. You could either multiply straight across and get 6 over 3 and then reduce to get 2. Or you can go a little bit of a shorter route if you catch these kinds of things. And you can realize, oh, I've got a 3 on the top, a 3 on the bottom, you just cross off and I'm left with that. But that's basically it. So the process doesn't change, you just have to remember how to multiply fractions. You can either do top times top, bottom times bottom and reduce, or you can cross reduce and then multiply. Either way works. So let's throw one of these at you guys. Let's say I gave you guys f of x is equal to 5 over 7 times x to the 10th power. Okay? Pause the video here and see if you guys can get the answer, and we'll work through it when you're done. All right, so derivative. We're going to multiply the 10 times the front. And we're going to take 1 off of the power. And we're going to think of that 10 as 10 over 1, right? Multiplying straight across. Notice I can't cross reduce here. 1 doesn't go into 5, and 7 doesn't go into 10. So there's no cross reducing this time. So all we can do really is just multiply straight across and get 50 over 7, x to the 9th. By the way, you could also write it like this. That would be fine as well. There's 2 different ways to write your answer, and I would encourage you to write down both because both of those can appear on a test. There's just different ways of writing the same thing. All right, let's go ahead and take a look at another one here really quick. But before we do, I want to talk to you guys about a shortcut for subtracting 1 from a fraction. Because you're going to be doing this a lot, and we don't want to go about it the long way. So first of all, I'm going to show you guys the long way, and then I'm going to show you the short way. Okay, so let's go ahead and start off with the long way. So let's say I want to subtract 1 from some fraction. So let's say that I have something like 7/3, and I want to subtract 1 from it. Okay, well the long way is, of course, first of all, to think of both of those things as fractions, and then to get them to have a common denominator. So if I multiply this fraction over here by 3 on the top and bottom, then I'll create an equivalent fraction that has the same denominator as the other one. And as soon as you have a common denominator, you can subtract them. But there's actually a much faster way to do it, okay? So here it is, 7/3 minus 1. First of all you do is you do top minus bottom. Well, actually, let me rephrase that. You're going to the numerator of your answer is going to be top minus bottom. So 7 minus 3. What is 7 minus 3? It's 4. That's my numerator, and my denominator will be the same as original. So the original was 3. So there it is. So it's a much faster way to find, instead of going through the trouble of getting a common denominator and stuff, you can just do top minus bottom and keep the bottom the same. So let's do another example really quick. Let's say that I had 3/7 minus 1. In this case, you had to do top minus bottom. What's 3 minus 7? 3 minus 7 would be -4, and you keep the bottom the same. There's your answer. So that's what 3/7 minus 1 would be. Why don't you guys try one really quick? Let's say I gave you guys 5 over 2 minus 1. Try to just do some mental math here really quick without pausing the video and see if you can just get the answer. You do top minus bottom, so 5 minus 2 is 3, and you keep the bottom the same, so it's 3/2. Let's do another one. How about 3 over 8 minus 1? Do that one mentally and see what you guys get. Should be -5/8. Okay, now that only works if you're subtracting 1. Just keep that in mind. If you're subtracting 2, it's not the same thing anymore, so you can't do that. But if you're subtracting 1 from a fraction, basically just do top minus bottom, keep the bottom. All right? And the reason why it's worth memorizing that shortcut is because you're going to be doing that a lot with problems like this. So let me show you how that comes in handy here. So I want to find the derivative of this function. Q of x is equal to 2x to the 2/5. Okay, so the first thing I'm going to do to find my derivative, change my Q to a G there by accident. The first thing we're going to do to find our derivative is we're going to take my 2/5 and we're going to multiply it to the front. Nothing new there, right? But here I want to subtract 1 from this. I don't really want to go through the trouble of doing 2/5 minus 1 by finding a common denominator doing the long way, so I'm just going to do the short way. I'm going to do top minus bottom, which is -3. 2 minus 5 is -3. And then I'm going to go ahead and keep the bottom as a 5, which it was originally. From there, the problem is pretty much done the same way it has been. You make both numbers a fraction, top times top, bottom times bottom, and you end up with 4/5 x to the -3/5. Okay, so I want to throw one of these at you guys now. So how about you guys do y is equal to 7x to the 3/7, we've already done that, 3/5 power. Go ahead and pause the video, see if you guys can get the right answer here, and when you're done, unpause it, and you'll see how to do it. Make sure you guys actually are pausing the video here. You working on this stuff is very important. Watching me do it is nowhere near as valuable as you actually doing it. So we're going to multiply the 3/5 to the front, and we're going to take 1 away from the power. To do that, we do top minus bottom. Remember, it's top minus bottom. It's not bottom minus top. So it's 3 minus 5, which is -2, not a +2. And you keep the bottom the same. We do need to simplify our coefficient here in the front. So think of that as 7 over 1. 3 times 7 is 21. 5 times 1 is 5. And we're good to go. Now, I want to share with you guys another pre-calculus fact. About negative exponents. This is a review. This is something that you should have seen at some point in the past. Anytime you have a negative exponent, you can make that a positive exponent by moving it to the denominator, by moving the entire term to the denominator and making it positive instead. Okay? Likewise, if you want to go back to this, you could just put it on the top and make it negative. Or just change the sign is another way of saying it. Okay? So, for instance, if I have this, that's the same thing as 1 over x squared. Okay? Or, if I have this, that's the same thing as x to the -7. One other little detail to keep in mind when you're doing this is if there's a coefficient there, like let's say I have 3x to the -3rd power, well, this 3 that you guys see here, that's a coefficient. That part is not going to change. That part stays in the numerator. It's this part that goes to the bottom. So the 3 will stay on the top, the coefficient, but just the x term will go on the bottom. And I forgot to make it a positive, by the way. So it's 3 over x to the third. All right. So now, knowing all that, let's go ahead and apply that here to this problem. Okay. So I've got 21 over 5 being multiplied by x to the negative 2/5. Well, I could just rewrite that like this, right? And then we can just multiply these together to make one big fraction, and we have this. This is another way to write it. And I would encourage you guys to write both because, once again, both of these can show up on your test. So you need to be aware of how to write your answer in either fashion. All right? So let's go ahead and move on to part E here. And let's do y equals 2 over x to the third. Okay. So the first thing you're going to do when you have a problem like this, some number over x to a number, then we're going to follow a 3-step process. First, we're going to rewrite it. So what do I mean by that? I'm going to take my function, y equals 2 over x to the third. I'm going to rewrite it. I'm going to keep the 2 where it is. I'm going to move the x to the third up to the top with the 2, but by doing that, I'm going to make the power a negative. So that's your first step. We want it. Why do I do that? Well, I want to turn this function into a power function. Why do I want it to be a power function? Because I'm trying to find the derivative. I'm trying to differentiate this. And I don't have a rule to differentiate this right now, but I do have a rule for power functions. So by changing to a power function, now I can apply the power rule. Now I want you guys to notice something very important here. Well, let me finish this first. We're going to multiply the power to the front. Negative 3 times 2 is negative 6. And if you take 1 away from a negative 3, what does that make? Careful. What is negative 3 minus 1? Think carefully. It's negative 4. It's not negative 2, right? Be careful there when you do subtract 1 from a negative number. Be very careful with those. All right, so there's my answer. Now this answer is technically okay, but we can do more with it. But before I go any further, I want to emphasize something. Compare this with this. What do you notice? One has a prime and one doesn't. Because the reason for that is because this is a derivative. This is not a derivative. That's just a pre-calculus method to rewrite the problem. This is exactly the same thing as this. It's just written differently. Okay? So I want you to understand we didn't do any calculus on our first step. We just rewrote it. And so there's no prime here because I didn't actually find the derivative. The prime shows up here after you actually apply the power rule where you multiply the number to the front and subtract 1. But anyway, this answer may show up on your test. However, you may need to rewrite again. So what do I mean by that? They may want you to put the negative 6 here, move the x to the bottom, and make that 4 positive. Either one of these are good answers. And you want to make sure you know how to write both. All right? So let's do another one of these. We'll do 2 examples of this one just to kind of make sure it really hits home with you. So let's say I had y is equal to 7 over 2x squared. Okay, so what are you going to do here? Pause the video and do step 1. I want you guys to rewrite this problem. That's the step 1, so that it's a power function instead. All right, so what we do with the power function is you're going to put that x on the top with its power, but you're going to make the power an opposite sign. The 2 is going to stay on the bottom. Okay? Now, go ahead and apply the power rule to this. Oh, I just made a mistake. That prime should not be there because I didn't actually find a derivative in this step. I just rewrote it, right? We've got to be careful with that. Now, want you guys to do step 2. Now I want you to actually do the power rule and find the derivative. So pause the video here and see if you guys can do it. It looks a little different than normal, so see if you can figure it out. All right, so what we're going to do is we're going to multiply this number times the front of our fraction. So it's going to be negative 2 times 7x over 2, and that I'm going to take 1 away from that power, which is now going to make it negative 3. Now, we've got to multiply fractions, right? So let's go ahead and multiply these fractions together and simplify it. Well, the 2's can cancel out, right? And that leaves me with the following. Negative, because that negative's still there, 7x to the negative 3. Now, I want you guys to do the last step, which is to rewrite it. I want you to rewrite this answer. What's another way we can write this answer? The other way we could write this answer is as negative 7 over x to the 3rd. You just put the x on the bottom and change its exponent's sign. Okay, so let's do another one. Let's say that I have 8 over 5x to the half power. 8 over 5x to the half power. Pause the video here and see if you can rewrite it. I did it again. I put a prime in. We're not supposed to put a prime there because I haven't taken the derivative yet. So we're going to put the x to the half on the top with the 8, but it's going to become negative. We're going to keep the 5 on the bottom. Now take your derivative and simplify it all the way. So take your derivative and simplify it as much as you can. So the first thing you would do is you'd multiply that negative 1/2 to the front. And you're going to take 1 away from your power. Now you got to be careful here. We have top minus bottom, right? So that's negative 1 minus 2. What's negative 1 minus 2? It's negative 3, and you keep the bottom the same, right? Now I'm going to simplify my fraction. That's going to be negative 8x to the negative 3/2 over 10. Okay, so that's one answer in simplified form. But what's the other answer? See if you could write the other answer down. The other answer would be negative 8. Oh, actually, I didn't simplify this all the way, did I? 8 and 10 can be reduced. I should have reduced that. 2 goes into 8 4 times. So I should have had negative 4x to the negative 3/2 over 5. That was my bad. Sorry about that. So rewriting that, we would have negative 4 over 5x to the positive 3/2. So those are the two ways that you can write these answers. All right. So this is getting kind of hairy. So I'm going to give you guys one more opportunity to practice. Oops. I'll change that up a little bit, actually. Go. All right, so go ahead and try that and see what you guys get. When you unpause it, you'll see the solution all worked out. All right, there you go. So in green, we have the rewriting process. In purple, we have the power rule. And then in red, we have the other way to write it. All right, let's go ahead and move on to part F. All right, so here's another pre-calculus rule. Another pre-calculus fact. If you have a function that looks like this, the cube root of some power function. Actually, let's not add numbers, let's just do letters. If you have some root of a power function, you could rewrite that as a power function where this number is the numerator and this number is the denominator of a power of x. Those are identical things, and you're welcome to go both ways. Okay, so that's, once again, we're going to follow that same format here of steps as we did for this one. We're going to follow the same steps here. Our first thing we're going to do is we're going to use the pre-calculus fact to rewrite it. Then we're going to do the power rule, and then we're going to rewrite it again. So, step one, let's rewrite it. Let's make it a power function instead of a root function. So here's my problem here for part F is the cube root of x to the fourth. So the first thing I want to do is rewrite it. So to do that, I'm going to put x here. This is going to be my numerator. This is going to be my denominator of the power there. The next thing we do is we do the power rule. So I'll put PR. And according to the power rule, we put 4/3 in the front, and we subtract 1 from the power. Now, we can technically rewrite this. What we could do is we could do 4/3, and I could rewrite this as a root, where this is my root, the 3, and this is my power, it's a 1. Okay, and you don't need to write 1 as a power, just so you don't forget. So this is an acceptable answer, and so is this, but there it is. So rewrite, power rule, rewrite, just like the last problem. So when you see problems like this where the power is in the bottom, or we see problems like this where there's a radical, you're going to have this 3-step process of rewrite, power rule, then rewrite. Okay. So let's give you guys a couple of these here. So let's say I gave you guys that. So first of all, before we begin, I want you to be aware that when you have a square root, there's not a number here, but there is. They just don't write it. It's a 2. Okay, so if they don't have a number there, it's a 2. So if you want to fill it in there, go ahead. So go ahead and do step 1 here. I want you guys to start by rewriting it. Pause the video and see what you get if you rewrite it. Here's what it would look like if you rewrote it. Now, apply the power rule. Pause the video and see what you get. So, applying the power rule, you should have gotten this. Now, I want you to rewrite it again. This time changing this thing into a radical of some kind. Well, the bottom number goes here, and the power goes here. Now, just so you guys know, though, you don't need a 1 as a power, and you don't need a 2 as a root. That's implied. So you don't have to actually write those in this case. If your root is a 2, you don't need to write it. If your power is a 1, you don't need to write it. And so there would be your 2 possible answers. Okay? Let me give you one that's a little bit more challenging here really quick. Try this one. See what you get. Go ahead and pause the video, go as far as you can, and when you unpause it, I'll go through it. Step 1 is to rewrite. Step 2 is to do the power rule. Now here's what's hard about this, is that we have a negative exponent in there, don't we? So the way we're going to deal with that is, first of all, I'm going to throw this whole thing into the bottom. So instead of having 2/5 x to the negative 3/5, I'm going to put the x to the negative 3/5 on the bottom now. And then we can actually write it like this as well. And there you go. So that would be a way to write it. Now technically this is a fine answer, this is a fine answer, and so is this, but you have to be able to be aware that all 3 of those are the same thing. All right? Let's go ahead and move on to G. Now, with G, I want you guys to be aware of something. You can do the power rule on this, but it's not necessary. This is a linear function, and we have a constant multiple rule for that. Anytime you have y equals mx, the derivative is just going to be m. Okay? So in this case, y prime is 9. It's that simple. Now I could show you the long way using power rule. You don't have to do this, but Here's a long way. Well, my x doesn't have an exponent. That means it's 1. So if I do 9 times 1, I get 9. And then if I subtract 1 from the power, I get 0. And anything to the 0 power is 1, and therefore 9 times 1 is 9. So yes, the power rule actually works on these, but why do that? We have a nice shortcut known as the constant multiple rule that we apply to linear functions. So if you ever see this, just know the derivative is just going to be the number that's in front of the x. Something similar here happens on part H. Let's take a look at that. We have a nice shortcut rule for that also, don't we? See if you could think about what that would be. What would that be? Hopefully you guys remember, anytime you have y equal to just a number, its derivative is 0 because that's a flat line. So y prime equals 0. And you could, once again, you could do the power rule again on this. It's completely unnecessary and not very helpful, but you could. Check it out. I'll show you. If you have y equals 2, well, isn't that the same thing as 2 times 1? And isn't 1 the same thing as x to the 0? We already talked about that. So now that I've got 2x with a power, I can do the power rule. 0 times 2 is 0. Take 1 away from the power. 0 times anything is 0. So you still get the same answer, but that's not helpful. So I would just say constant, make it 0. All right? Okay. Let's go ahead and move on to a new topic here, a new type of example problem. So this problem is asking us to find the instantaneous rate of change of the function, in other words, find the derivative, at an indicated value this time. So instead of just finding the derivative, we're actually going to plug a number into it and get an answer which will tell us the slope of our line at a specific point. So up till now, we've just been finding the derivative, which is a function. But if you actually plug a number in for x, that will tell you what the slope is at that point, and that's what we're going to do now. We're also going to sketch the tangent line, okay? So 3 things that we're going to do on each one of these. We're going to find the derivative, we're going to plug a number in to find the instantaneous rate of change at that specific point, and then we're going to sketch what the tangent line would look like. So here's my function that I'm going to be finding the derivative of, and here's that function's graph. So let's go ahead and begin here, number 1. F prime, in parentheses we have -2. So this means I'm going to find the derivative, and this means I'm going to plug in -2. So let's do that. So first of all, if I wanted to find the derivative of this function, let's apply our power rule. I'm going to multiply this 2 times the front. 2 times a -1/2 is -1. And then I'm going to subtract 1 from the power, and I'm going to get x. So there's my derivative. It's -1 times x. All right? So I wanted to find my derivative, but now I also want to plug in 2. So I'm going to plug 2, and I'm sorry, not 2, -2. I'm going to plug -2 into this problem. -1 times -2 is a +2. Now what this means is that for this blue line down here, the slope of the function at x equals -2 is a slope of 2. So let's graph what that means. So first of all, we want to find this value of x on the blue line. Can you guys find on the blue line where x equals -2? Right there. That's the point on the blue line where the x value is -2. Okay? So there's that. Now, can you guys sketch what a tangent line would look like there? What would a sketch of a tangent line look like there? Well, hopefully you know it looks something like this. Okay? It just grazes this point right here, which is called the point of tangency. It just grazes it, okay? And therefore only touches the curve at that one single point. Now, there's a way we could be a little more specific, though. Since I know what the slope of my function is at -2, I know it's 2. Starting from here, I can just go over 1 up 2 and get a nice looking graph there. So there it is. All right? So at x equals -2, this function, f of x, has an instantaneous rate of change of 2. Or in other words, the slope of this blue line at x equals -2 is 2. Let's do another one. Let's go ahead and move on to part 2 here. Now on this problem, this is just another way of writing the derivative. So I want to find the derivative of my function first, which we've already done, right? That's not going to change. the derivative of this function with respect to x is negative 1x. We did that on the last problem. That step's not going to change. I'm just using different notation this time. But now I want to plug this number in. So I don't want just a derivative. Now I want to find an instantaneous rate of change at a specific point. So if I were to plug in 0, let me write that, we say df dx at x equals 0. That means I'm going to replace the x with 0 and solve. So I get 0. So the slope of my function at x equals 0 is 0. So let's sketch that tangent line now. Can you guys find on this graph where x equals 0? Can you sketch the tangent line at that point? What would that tangent line look like? Well, just by eyeballing it, it would have to look something like this, right? But you can also use your answer up here to make sure you're right. My slope should be 0. And that's a flat line, right? Flat lines do have a slope of 0. So there you guys have it. All right, let's go ahead and do the last one here. The last one, instead of giving you symbols, I'm using just different notation. It says, find the instantaneous rate of change at x equals 1. So if you want to find the instantaneous rate of change, that means you need to find the derivative. Once again, we've already done that, and you can use whatever notation you want to at this point. But either way, we already know that the derivative is negative 1x, right? But they want us to find the derivative at x equals 1. So see if you can figure out what would the instantaneous rate of change be at 1. See if you can do it in your head. Well, to find what the instantaneous rate of change is at 1, all you would have to do is plug in 1. And you get negative 1. So that means at x equals 1, f has a slope, also known as an instantaneous rate of change, of 1, negative 1, I'm sorry. So see if you guys can graph it. This is important you guys practice graphing these things because you're going to have to do it on your test. So see if you guys can graph this tangent line. Pause the video and see if you can do it. You have to find where the value of x equals 1 first, put a dot there. Then you're going to sketch a tangent line, and it should have a slope similar to that one. See if you guys can do it. So here's where x equals 1, and if I were to sketch a tangent line, it would look like this. Now, we don't have to worry about being too precise. I don't care if you get your rise and run exactly right, but what should match is the following things. Here's how I'll be grading you on these when you graph your tangent lines. Does your tangent line touch the x value that it's supposed to? Does it look like a tangent line? Does it really only touch the curve at one point, or are you being kind of sloppy and drawing it so it hits 2 points on the curve like that? We don't want that. So, does it touch the point of tangency? Is it actually tangent and not secant? And then finally, is it going in the right direction? If you have a positive slope, it should be going upwards. If you have a negative slope, it should be going downwards. If you have a zero slope, it should look relatively flat. So I'm not going to be counting your rises and runs to make sure the steepness is just right, but I will be looking at whether you have a positive slope or a negative slope. It should match your answer. Okay, so let me go ahead and throw one at you guys. Go ahead and pause the video here. And when you unpause it, I'll have the solution for all 3 of these up for you guys to check your work with. Don't forget, you're finding the actual value of the slope and you're sketching the tangent line. You're doing 2 things. Okay, so let's go ahead and go over our answer. First of all, I found my derivative. Hopefully that's what you guys got for your derivative when you applied your power rule, so 1/3 x cubed. The next thing I did was I did the first one. They asked me to find the instantaneous rate of change at x equals negative 1. So I'm going to plug negative 1 into my derivative function, x squared. So negative 1 squared is 1. And so I should have a slope of positive 1 at x equals 1. And so you guys can see over here the green line. That line has a positive slope because it's going in an upward direction. And it's touching the curve at one point, and that one point is at x equals negative 1. So that's what that tangent line should have looked like. We're going to continue that process now with the rest of them. So same thing here, just asking you to find the derivative and then plug 0 in. So my derivative is x squared, so when I plug in 0 and I square it, I get 0. So that means that at x equals 0, I should have a slope of 0. And that would be right here at x equals 0, and there's my 0 slope. It's a flat line. All right, last one here. Once again, we're just finding the derivative of the function at 1. So 1 squared is 1. And so at x equals 1, I should have a tangent line that touches the curve at just that 1 point. And it should be a positive slope, moving in an upward direction because I have a positive 1 for a slope. Right? And there you guys have it. So that's going to do it for us today. So today we learned 3 rules: the constant rule, the constant multiple rule, and the power rule. All 3 of these are ways to find derivatives of specific functions, which are basically functions that tell us how to find the slope of a function at a single point. All right, we'll stop there, and we'll see you guys in class.